Here we'll wrap up Chapter 8 by examining the valence shell electron pair repulsion model, or VSEPR model, which helps us to predict molecular geometries and bond angles. Molecular geometries are key to a molecule's function. Subtle differences in geometry can render a molecule highly toxic. Now, while there are many accurate methods for determining molecular structures, it's often useful to make predictions using a model, such as the VSEPR model. VSEPR stands for valence shell electron pair repulsion, and here the structure around a given atom is determined principally by minimizing electron pair repulsions. So electrons are negative, they will repel each other. Chemical bonds, covalent bonds, which contain electrons, will spread themselves out so that they minimize those repulsions. There are a few steps to applying the VSEPR model. The first thing we need to do is draw a Lewis structure for the molecule, make sure that the octet rule is obeyed, make sure that we distribute all of our electrons. Then we count the electron pairs and arrange them in a way that minimizes the repulsions between electron pairs in bonding groups and non-bonding groups. We put the pairs as far apart as possible. Then we determine the position of the atoms from the way the electron pairs are shared. This is how electrons are shared between the central atom and surrounding atoms. And then we determine the name of the molecular structure from the position of the atoms. So a few of the various geometries that we'll look at when we have two groups of electrons around a central atom, such as in beryllium dichloride, we have minimized electron pair repulsions by arranging those two groups of electrons in a linear fashion, which means that the bonding pairs of electrons are 180 degrees from one another. When we have three groups of electrons around a central atom, as we do in boron trifluoride, we can minimize repulsions between those bonding groups of electrons by keeping them at 120 degree bond angle from one another. This is known as a trigonal planar geometry. When we have four groups of electrons around a central atom, as we do with any carbon-containing molecule with four single bonds, we can minimize electron pair repulsions in three-dimensional space by arranging a tetrahedral geometry with 109.5 degree bond angles. Here, some of the electrons or bonding groups are sticking out at us and others are going away from us. This is not a square planar geometry, this is a tetrahedral geometry. Now when we look at ammonia, we have four groups of electrons around the central nitrogen, but only three hydrogen atoms. So the arrangement of electrons shown in A is tetrahedral. There are four. However, because one of those groups is a lone pair, we only see the hydrogens and nitrogen in a trigonal pyramid geometry, as is shown in C. The molecular geometry would not see the lone pair of electrons because it is not an atom. Likewise, for water, we have a tetrahedral arrangement of electrons around oxygen, as is shown in figure A. But because oxygen is bound only to 2 hydrogens, as is shown in B, the molecular geometry of water is bent or V-shaped, as is shown in C. Now let's look at the bond angles in methane, ammonia, and water. In methane, we have a true tetrahedral geometry with 109.5 degrees bond angle. In ammonia, we have a slightly contracted bond angle of 107 degrees. We no longer have a true tetrahedral molecular geometry. We have a tetrahedral arrangement of electrons. Remember, there is a lone pair on the nitrogen, but we don't have a true tetrahedral molecular geometry, as is evidenced by the 107-degree contracted bond angle. In water, our bond angle is contracted to 104.5 degrees from tetrahedral 109.5. Remember, there are 2 sets of lone pairs on our oxygen in water. The reason that we get this contracted bond angle in ammonia and in water is shown here. In figure A, we have bonding electrons between element X and hydrogen. The bonding electrons are shared between 2 nuclei, and so they're spread out. In figure B, element X has a lone pair of electrons which sit very close to element X. This causes any other electrons attached to element X to contract from normal bond angle. So let's review some of the geometries that we've seen. With 2 electron pairs around a central atom, we can minimize repulsions with a linear geometry and a 180-degree bond angle. With 3 pairs of electrons around a central atom A, we can minimize electron pair repulsions with a trigonal planar geometry and 120-degree bond angles. With 4 pairs of electrons around a central atom A, we can minimize repulsions with a tetrahedral geometry and 109.5-degree bond angle. With 5 electrons around a central atom A, we can minimize repulsions with a trigonal bipyramidal geometry where we have 120-degree bond angles around the center and 90-degree bond angles at the axial positions. With 6 groups of electrons around a central atom, we can minimize repulsions with an octahedral geometry where we have 90-degree bond angles between all electron pairs. Now, when we have a tetrahedral electron arrangement, but lone pair electrons on our molecule, our molecular structure becomes different than the tetrahedral. With 1 lone pair of electrons, we have a trigonal pyramid. With 2 lone pairs of electrons, we have a V-shaped or bent molecular geometry. When we have 5 groups of electrons around a central atom and we begin having lone pairs, then we go from having our trigonal bipyramidal molecular geometry to a seesaw molecular geometry with 1 lone pair, a T structure when we have 2 lone pairs, and a linear molecular geometry when we have 3 lone pairs. Keep in mind that here the electron arrangement is trigonal bipyramidal. So we have multiple arrangements for electron pairs in something like triiodide ion. In figure A, we have 90-degree bond angles between our lone pair electrons. In figure B, we still have 90-degree bond angles between our lone pair electrons. In both of these figures, we have probably 104 and 107 degree bond angles between our iodides. In figure C, we have minimized electron repulsions with that linear molecular geometry. Our lone pair electrons now have 120 degree bond angles between them. Our bonding electrons are at 180 degrees. When we look at xenon tetrafluoride, we have two different arrangements for our fluorines around xenon. We can go with a seesaw, shown in A, or with a square planar arrangement shown in B. Our square planar arrangement gives us 180 degree bond angles between our lone pair electrons on xenon. This minimizes repulsions and leads to a more stable square planar molecular geometry. Now there are other methods besides computer-generated drawings to show molecular geometries. Molecular model kits are readily available. We can show a linear arrangement with 180 degree bond angles. We can easily show a trigonal planar molecule with 120 degree bond angles and 3 groups of electrons. We can also show tetrahedral molecules with 4 identical bonds and 109.5 degree bond angles with our molecular model kits. Coincidentally, when we tie 4 balloons together, they naturally form a tetrahedral shape.